we can start. So today we are going to look at data analysis before we can proceed on to deploying our model, because we'll need to deploy a model that has got an analysis part backing it. So we will be using Colab for analysis. So open colab.research.google.com and then create a new notebook. So that's where we will be doing all these code work. And then for our data set, we will get it from Kaggle. I'll try to get an updated data set. So I'll click on datasets. I can click on all datasets, and then I'll filter it by, let's say, new. Let me check data that we can use for today. We've got these cells dataset, so these should be for regression tasks. Let me check for classification. Let's have a look at these disease symptoms. We've got no description about the dataset, but this is how the dataset looks like. We've got the index column, patient ID, the age of the patient, the gender, the temperature. We've got the humidity. We've got the wind speed, season, nausea, joint pain. But we've got no target column. So this is, or maybe the target column might be joint pain, though we have lots of class imbalance over here. Let's try look for another data set. Let's have a look at this credit card fraud detection system, data card, and then data set. This is a IPYNB file. It's actually not a data set. Let's go back here. I'm trying to find a data that we can use for today. It will be something new and unique, so you'll see how we approach our data analysis projects. Let's have a look at this online fraud detection dataset. Yeah, so steps, payment in, imbalance. This data is not okay. Let me close a few tabs over here and we can try and find new datasets. So I'm trying to find a dataset that we can use for today. Just give me a minute as I'm checking this. Okay, so this dataset might be good, the breast cancer prediction dataset. Let me download it and inspect it on Excel. I'll upload it to GitHub and then I'll share the link with you. So breastcancer.csv. Okay, this is what we have. So we've mentioned that the status, what we're trying to predict is whether this individual is alive or dead. So this is the kind of data that we can work with in this case. Let me upload it to GitHub and then we can start the actual data analysis. So dashboard here, I'll create a new repository and the repository will be breast cancer prediction. Then add a readme file, then I'll create repository. I'll upload the dataset here. So I'll click add file, upload files, choose your file, and then I'll pick the breastcancer.csv file. If you want to have a look at more details concerning this data, it's available on that link. So for analysis purposes, I'll share the link to the dataset directly from GitHub. So I'll open the breastcancer.csv file and then I'll view raw. So this is the link that we'll use to load in the data. So have that. I'll need this page first of all to at least know some of the data descriptions that we'll need. So let's start our analysis. So for our analysis, it should be breast cancer prediction. And this is a classification problem. Okay. Let me share this notebook with you as well, so that just in case you need to copy what I'm typing in directly, you can copy it from the notebook. You just refresh it and you'll see the changes that I'll have made. So that's the link to the notebook. We can begin. So I'll connect and then we can begin. So up here at the top, we are going to start by defining what we are going to do. So breast cancer prediction. So in this case, we are going to create a model that can predict if an individual will be alive or dead in the next checkup. So that's what we are basically checking. And for analysis, we usually start by importing libraries that we need. So here we'll have import libraries. So we'll import pandas as PD. We'll import NumPy as NP. Then we'll import Seaborn as SNS. Then we'll import matplotlib. .pyplot as PLT. So those are the basic libraries that we need. Then we can import sklearn libraries. So from sklearn.model selection, we'll need the logistic regression model. We can fit a logistic regression model as the base model, and then we can improve this by fitting a random forest model from sklearn.ensemble, import random forest classifier. Then we can have accuracy score, we can have the conversion matrix, and then we can have the classification report. So all these are the libraries that we'll need for this task. So I'll run that and I'll give you 2 minutes to do the libraries importation and then we can proceed. So this is the link to the data. And then on GitHub, we have the link to the raw data. So have a look at that. And then in the next 2 minutes, we proceed. If you've got a question, you can ask. Okay, let's proceed. So the next thing we're going to do is we're going to import our data file. So we're going to have df being equal to pd.read underscore csv, open brackets. Then I'm going to copy this link that I shared with you in the chat. And then what we're going to do is we're going to check our data set top 5 rows. So we'll have df.head. So a minute you run this and confirm if you have the data on your end with a thumbs up in the chat. Is the data loaded on your end? Okay, let's proceed. So over here, what you usually do first before you can proceed is you usually check your data set. So over here, we will do some data checks. Okay, and in data checks, what we are doing over here is we're checking for missing values. I've reshared the dataset link in chat. You're checking for missing values, you're checking for duplicates, then you're checking for inconsistencies, then another thing you're going to do is you're checking for outliers. So those are the checks that we usually do. So we will start by checking for duplicates. And for duplicates, we usually type in df.duplicated.sum. Then you can see we have one single duplicate in the data. And then next we can check for missing values. So for missing values is df.isNull.sum. If you have a look at that, you can see that this data is clean and it has no missing values. So a minute you run these two and then we can proceed. So let's proceed. So the next thing is checking for inconsistencies. So for inconsistencies, so checking for categorical values. Issues. Okay. So for inconsistencies, what we usually do is we can start by typing in df.info. So over df.info, you can see we've got some columns that are categorical and some numeric. So over here, what we are going to do is we are going to create df categorical just for checks, and it's going to be df.select underscore d type. Then we are going to include only objects. And then if we check df.categorical.head, you can see we have only the categorical values. So to check for issues, the first thing we can do is, so for categorical, we can use a for loop. So for categorical, for call in df categorical.columns, print, then we print the unique values in each and every column. If we run this, you can see for race we've got white, black, and other. So this means the data is okay. For marital status, we've got married, divorced, single, widowed, and separated, which is okay. T stage, we've got T1 up to T4, N stage, N1 up to N4. Six stage, we've got those. Then differentiate, we've got all those uh, different levels. Then for grade, we've got grade 3, 2, 1, and a plastic grade 4. Then all these other variables that are here. So this basically means that what we are looking at over here is okay. So the data is okay, right? So for categorical columns, we have got no issues. Next, we can check for outliers in numeric columns. So check numeric columns. But I believe for numeric columns, there wouldn't be a need for us to check for outliers because it seems okay, but it's necessary we do it. So here, what we are going to do is plot, we're going to plot box plots for numeric columns. Okay, before I proceed, I'll give you 2 minutes to copy this code. I've shared it in the chat and run it on your end. One more minute. So let's move on to the next step. So for the next step, we are going to plot box plots for the numeric column. So we are going to have df numeric being equal to df dot select underscore d types. And here for d types, we are going to include float 64 and int 64. Then we are going to use Seaborn to do these plottings. So I'll add a palette and I'm going to use the Viridis palette. Let's run that. Got an expected argument. So CMAP doesn't have a. So data should be equal to df numeric, then column is equals to x dot column. Let's run that. So this is what we have. You can see for this is the block box plot that is being generated, and this is the first check that we usually do to see if the data has any outliers. So for age is running from 30 to 70. You can see the mean age is around 54, let's say, and we've got no outliers when it comes to age. Then for tumor size, most of them are running from 0 to 0 to 60, let's say 70. And then we've got some outliers coming in at 80 to 140. So these are some of the things that you can explore out later on and see if they should remain in the data or if they should be removed. Then regional node examined, as same here, we've got some outliers ranging from, let's say, 35 to 60. And then for regional node positive, we've got outliers ranging in from, let's say, 10 to 40. So these are some of the things that you'll need to check. And then survival months, we've got 0 to 10, let's say 0 to 5 months being considered as outliers because most of the individuals survive, let's say, 10 to 100 months. So for outliers, I won't deal with them for today, but I'll leave that to you as an assignment on how you can remove those outliers or how you can examine and see if they are relevant to be left or if they are supposed to be removed. So I'll copy this code, share it with you in the chat, give you 2 minutes to copy these and run the code. So the next thing we are going to look at is EDA. We're going to have maybe 5 different questions on this specific problem, and we're going to answer them using plots on the EDA part. So remember what I'm creating over here is something a little bit basic, but if you've got time, you can create something even more advanced with in-depth analysis. If you've got a question, you can unmute and ask. So 2 minutes, you copy this, and at 8:36, we are going to proceed. Yes, Johan? Yes. Numeric columns. It's only for numeric columns. Okay, apart from this, there is another way you can check for outliers. So here you can check for outliers using the Z-score. Okay. And you'll have to use the SciPy library, and you'll have to set a threshold and then print out if you have any outliers. So let me check. This is just an extra. You can use the z-score to check for outliers. So this is something that you'll check out later on, but mostly we usually use the box plots. So 1 minute is done. Let's move on to the EDA part. EDA. And over here, we'll need to answer a few questions. So the first question that I'm going to look at, let me be guided by my data. So df.head. So the first question that we'll need to have a look at is what is the distribution of the target variable? Okay, so distribution of the target variable. Then question number 2, we can look at maybe the tumor size, because I believe cancer survival, whether you are dead or alive, will be dependent on the tumor size. So what is the, so we'll have tumor size by survival status. What else can we look at? We can look at, I see we have got some hormones over here. So we can look at estrogen status by survival state, estrogen status by survival status. So we compare the two, and we can compare also progesterone status by survival status. And lastly, we can look at something else. Let's look at these categorical variable that we have over here, like the 6th stage by survival status. So what 6th stage of cancer will you be considered as dead or alive? So those are the things that we are going to look at. So first of all, let's look at the distribution of survival status. So for the distribution of survival status, we can actually create a Seaborn box plot, not box plot, but a count plot. So we'll have SNS dot count plot, and then our data should be equal to df. Then our x should be equal to status. Our, I don't know if we usually have a palette. So palette should be equal to Viridis. I like you saying Viridis a lot. Then we can add our plot title, and then we can show the actual plot. If we run that, we can see the actual distribution. We can see that majority of individuals that we have in this data are alive, and only a few of them are dead. So this is data set that is not balanced. So here, what you can do is you can explore ways of balancing the classes. But this is after you've fitted a model. So you can do things like oversampling. So oversampling means that you are going to increase the number of dead status. You're going to duplicate some of them to be equal to their live status. You can do undersampling. And in undersampling, you're going to basically reduce the class with more samples to match the class that has a less number of samples. So this is the distribution of survival status. So we've seen that class alive has more members than those who are dead. So let's move on to the next thing. We are going to have a look at what else. So there is tumor size. Let me see if there is a column that I had missed that is of great importance. I believe age. Yeah, age will be important over here as well. So let's add age to this analysis, and it can come in second. age distribution by survival status. So we'll need to compare how does age affect you being alive or dead when it comes to cancer. So for age, we are going to do a histogram because age is numeric and we've got different ages. So first of all, you can check the distribution of age, but over here we are going to do a combination of age and the status. So we are going to plot the distribution of age. So here we're going to have SNS dot, let's start with dist plot. I believe Seaborn changed that to dist plot, but let me use the older version so we can ignore any warnings that might appear. So data should be equal to df, x should be equal to age, then hue should be based off the status. What else do we need to add over here? So we'll need to add a KDE. Let's say KDE should be equal to true so that we can actually have a line that shows us what the distribution looks like. Then we can add our color palette and then a title for that plot. Let me run that. This plot got an expected argument data. Let's change this to hist plot. Yeah, so this is what we have for the histogram. We can see that for most individuals who are alive between age 45 and let's say 55, but they are spread out. So let's say from 45 to 60. So this is where most individuals are alive. But for majority of the individuals who are dead, we've got two different points. So between age 45 and 50 and age 65 and 70. So this is where a majority of the individuals who are dead are at. Okay, so this is in line with actual real world data. So we can say that age is not directly linked to cancer. Okay, but if we were to comment on this, we will say that survivors of cancer tend to mostly be young, because you can see for individuals who are between age 30 to 45, the number of deaths are quite low. But once you get to the 50 to 65 levels, the death toll based off cancer increase. Okay, so here we can say that there is a slight shift in age distribution for those who have survived once you are old. So you can see it's a little bit constant over here, but from younger ages it's going up a little bit. So this, for the dead, this will be your main focus. So that's the comment for this part. Let me share this code and then I can give you a minute or two to replicate these two plots, and then we can proceed on to the other plots. Anyone with a question? Yes, John. Yes. No, not really. It won't be clear. You'll create those charts based off the problem statement that you will be given. It's easy. You won't miss a thing. So don't worry about that. Okay, one more minute. Let me get some water and then we can proceed. let's proceed. And next, we are going to look at tumor size by survival status. For tumor size, let me confirm what we had. For tumor size, we created a box plot. So we can replicate that. Instead of creating a box plot, we can create a violin plot. Here we can have tumor size versus survival. We can have SNS dot violin plot. Then data should be equal to df, x should be equal to status, y should be our tumor size, then palette is where it is. Then we can run that. I could not interpret tumor size, so I believe that name is incorrect. So df.columns, yeah, this is the correct naming for tumor size. Okay, so we've got two violin plots over here. So one is for those who are alive, and one is for those who are dead. So you can see the violin plot for those who are dead is a little bit big as compared to those who are dead. Okay, so this, what we are seeing over here is for those individuals who survive. Okay, their tumor size is a little bit small to those who don't survive. If we head a line, let's say at level 25, you can see that the tumor size for those who are dead, the mean is around level 25. But for those who are dead, the mean is around level 25. For those who are alive, it's down here. Let me see if I can add something over here. SNS dot swamp plot. Let's run that. See if it will be added to the plot. Hoping we won't get an error, because that will be able to show us where the data points are concentrated mostly on. It's taking time to load, which means I might have an error. Let's wait and see. Let me stop it and delete this. So this is our violin plot. It's telling us that for individuals who are dead, their tumor size was a little bit big as compared to those who are alive. So this white line that is in the middle of this black part, so this is in the middle, what we have is actually the box plot. You can see that the mean is low for those who are alive, and the mean for tumor size is a little bit high for those who are dead. So it means that the bigger your tumor size is, the chances that you are not going to survive. So that's what we have. Let me copy this code and share it with you in the chat. I've sent it, and we can look at the next thing, that is estrogen status by survival status, and then progesterone status by survival status. So let's start with this. Here what we can have is a count plot. So count plot will do. We can run that. Here we can see the difference between the positive and negative classes. So if you've got estrogens, let's say your status is positive, then it means you'll have a higher chance of being dead. Then if it's negative, you'll have a higher chance of being alive. So positive oestrogen causes are strongly associated with survival as well, because you can see most individuals who are here. Actually, if we look at this plot, the correct way to interpret it is if you've got a positive oestrogen status, then it means you are highly likely to be alive, because you can see the distribution of those who are alive and those who are dead in the positive class for estrogen is quite imbalanced. So we can say more than 80% are alive, while let's say 15% are dead. But when it comes to negative status for estrogen, the classes are almost at par. So it means that if your estrogen status is negative, then you have a higher chance of being dead than alive, as compared to you having a positive estrogen status. So we can say estrogen is a little bit linked to survival. Then next we can have a look at progesterone status. And here we can do a bar chart as well. So count plot, and the same here we have the same results as estrogen status, but a little bit more defined. So for progesterone status, it means that the chances of you being alive have reduced by a smaller margin, and the same has happened over here for the chances of you being dead. It has if your progesterone status is negative, it means that your chances of being dead have reduced a little bit, because you can see over here in the negative class, we have we now have a little bit of a wider gap. So that's what we have over there. So that's how we can interpret it. Then lastly, we can have a 6th stage by survival status. And for 6th stage by survival status, we can do a box plot as well. Not a box plot, but that count plot, because it's a categorical variable. This is what we have. You can see the different statuses and the different things that we have. So we can start with IIAA. So for that, you are most likely to survive, because you can see those who are alive are many as compared to those who are dead. Then for these two stages, IIA and IIC, you've got increased chances of being dead. For IIB, you've got increased chances of being alive. And triple IB, here you've got increased chances of being dead, but most individuals never get to this stage. So that should be it for EDA. We don't have to look at much. So the next thing we are going to do is we are going to do the modeling. And for modeling, this is where we actually create our machine learning model. So I'll give you 3 minutes to at least redo what I've done over here. It will be easy because you're using Google Colab, and then we can proceed. So at 8:58, we are going to fit our model. And remember, everything that we are fitting over here, we will include it in our deployed web application. So have a look at that, and at 8:59 we are going to proceed on with the modeling part. Okay, let's proceed and fit our ML model. Remember, we imported logistic regression for the base model. Yes, Daniel, I can see your hand raised. Yeah. Okay, so this is your violin plot for alive and dead individuals. So for the violin plot, what you are basically checking is the distribution. If let's say if we what can I use to hide one of the parts of this? Let me take this. Okay, so if we let's say hide one of the sides of the violin plot that we have over here, we are left with something that looks like this. So this is a, let's say, a normal distribution curve. Okay, and for this normal distribution curve, do you see this white dot over here? This is where your mean is at. So when you are looking at individuals who are dead, you can confirm that the mean is a little bit high compared to those who are alive. So it means that the tumor size for those who are dead is usually big as compared to those who are alive. And another thing you can spot as well is for the tail of the violin curve is for those individuals who are dead, the tail is a little bit longer and you've got more individuals on that tail as compared to those who are alive. So for those who are alive, you can see that the distribution is fast going up and fast going down, and then the tail is short. But for those who are dead, it's, let's say, fast going up, then it's taking time to uh, go down because most of the individuals who are dead means they had big tumor sizes. So that's basically how you can interpret this violin plot. Is that a little bit clear? Yes, thank you. Okay. So let's begin. Here we are going to fit our base model. And for the base model, it's the logistic regression model. So here we're going to instantiate the model. Our LR should be equal to logistic regression. Yeah, so logreg should be equal to logistic regression. Then we fit the model. Actually, I should first of all split this data into training and test set. And before splitting the data into training and test set, we'll need to encode categorical variables. So split data into features and target. So our x should be equal to df dot drop, and then we are going to drop the status column. Axis should be equal to 1, and then our y should be equal to df, then we select the status column. And then what we can do is we can encode the data we'll have from sklearn dot preprocessing import ordinal encoder. So I'll use ordinal encoder. Then we're going to have encode being equal to that. And then, yeah, that should be okay. So X, let me see what we have on X encoded. Yeah, so we'll need to add our columns because I believe ordinal encoder removes the column names. And then after we've had that, we are going to split data into training and test set. So we're going to have our X train, comma, X test, comma Y train, comma Y test being equal to train test split. Then we get our X encoded and our Y variables. Let me confirm this from the documentation if it's correct. X train, X test, Y train, Y test. Okay. So test size means that 20% of the data will be used for testing and then 80% for training. Then random state is equal to 42. If you use 42, it means that the values that you're going to get will be same as mine. I'll run that. Let me copy this code and share it with you in the chat. The code is available in chat. In 2 minutes, you can copy that and then we can proceed. Over here, I'll complete this part. So we're going to have logreg.fit xtrain on ytrain. Then we can get our ypred. And then, yeah, next we can do the evaluation. So those are the two codes that I've shared with you. So run them, and then in the next 2 minutes, we're going to evaluate this model and then fit a random forest model and compare the two and see which one had the best results. Okay, let's proceed. We now have our model and the data ready. What we can do now is we can evaluate. So here we're going to have our conversion matrix being equal to conversion matrix. And then we pass in our ypred. And then we confirm this with our ytest. And then what we are going to do is we can run sns.heatmap. Then we can plot that conversion matrix. And apart from that, we can print the classification report. So for classification report, we pass in our ytest and ypred. Yeah, so I should interchange these. So y actual versus ypred. So this is our conversion matrix. This is the true positive, true negative. So it means that our model is not 100% accuracy, but when predicting class 0, it's okay. Then for the classification report, we can have a look at the precision and recall. For those who are alive, the model is perfectly fine at doing those predictions. You can see the precision is at 91% accuracy and recall at 98% accuracy. But for those who are dead, the model is not that great. It has an 80% precision score and a 47% recall score. So for the combined scores, it has a 59% accuracy. So if you're trying to predict if someone will be dead, then it means for this model, you'll have a 59% accuracy. I'll copy this code, I'll share it with you in the chat. I'll quickly fit a random forest model, and then we can compare the random forest model with the logistic regression model. So over here, we'll fit a random forest model. So we'll have ref being equal to random forest classifier. Then we can have number of estimators being 100 and all that. We can have our widespread being equal to that. And then, so this should actually be equal to widespread RF, so we can differentiate between the two. Then this is widespread. So widespread RF, and then we can do the same evaluation over here. So instead of widespread, we can have widespread underscore RF for random forest. Then here it should be widespread RF for random forest. If we rerun that, you can see that the accuracy has increased a little bit for class dead. It has gone up from 59% to 64%. So how can we further improve this? So you can do things like class balancing, and you can do things like hyperparameter tuning. So what I can quickly do over here, I believe these parts you are okay, you are good at fitting models, so I don't have to share this code a second time. So what we are going to do over here is we are going to do hyperparameter tuning. So for hyperparameter tuning, we'll have to import grid search, or let's say randomized search CV. So we're going to have from sklearn.model selection import randomized search CV. So randomized search CV is usually more fast as compared to grid search CV. Then what we are going to do is we are going to define our parameter grid. So param grid will be equal to, and then we can have number of estimators. Here I'll maybe start with 50, 100, 150, 200, 250, then 300. Then max depth we can have 2, 5, 8, 10, 15. What else can we add here? So let me look at random forest. Random forest hyperparameters. Let's just complete this using maybe Gemini. You don't have access to this. This is a feature that I exclusively have because it's something that I've been given access to by Google for testing. But for you, you've got the Gemini code over here. So I'll accept and run. Let's see what we are going to get over here. So hyperparameter tuning usually takes time to run, but let's see how long it will take over here. In the meantime, you can be asking questions if you have any. So it's done. We've got the best hyperparameters over here. Best accuracy 0.9024. Best accuracy 0.91. Still not okay, so it means we'll have to do class balancing. So that's something I'll leave you to explore. That's what we have for the hyperparameter tuning. You'll have access to this once I share the notebook. And then the last thing we can do is we can plot feature importance. So we'll have the variable feature importance being equal to a ref. Then we extract our feature importance. Then you can sort out the feature importance and then you can plot them using Seaborn. So these are the most important features when it comes to predicting if you are dead or alive. So survival month is at the top, age, tumor size, then regional node examined, regional node positive, marital status, sick stage, and all these other features are not that much important. So you can come up with a cutoff of, let's say, 0.05. So you can pick these 1, 2, 3, 4, 5 top 5 features and then refit the random forest model and see if it's going to give you a better accuracy or not. So I'll give you 3 minutes to maybe open the link for the notebook, go through each and everything that I've done and ask questions if you have any. If not, we are going to call it a day, and this will be our analysis file, and we'll basically use it tomorrow when we will be deploying this project on our front-end web application. Remember, if you share this code with someone who is not technical, he will not be able to understand what you've done over here. But for someone who is non-technical, sharing the link to your deployed web app will be the best option for them. So that's what we are going to do for today. But we needed to have an analysis file that would back up that deployed application that we will be building. Yeah, so 2 minutes, you have a look at everything through the link that I've shared, and then we can call it a day if you've got no questions. Yes, Joanne? Yes. Uh, it's recommended at times because you'll get to know which are the most essential features that are contributing more to changes in your target variable. So it's okay. You can plot this before you proceed. Actually, what you can do is you can have a chi-square plot that is using the chi-square distribution to plot feature importance. And you should get something similar to this. Let me see if it's something I can do. So Yeah, so this is what you have. You can see for chi-square, it's telling us 6 stage, N stage, T stage, and all those are the most important features. But it has done it for only categorical columns. Yeah, but you can do plots like this to define variables that you can continue working on the EDA part. So this is for categorical columns. Let me see if we can do one for numeric columns. I'll copy everything that we have here. I'll paste them down here. I'll remove this. And then here we can pick X encoded as a whole. Does not match a length of 10. Yeah, so you can see for chi-square, with all the data sets, it's giving us something similar to random forest: survival months, regional node positive, tumor size, 6 stage, N stage, and T stage. If we compare it to what we had, survival month, age, tumor size, and then the others are coming in. So just a slight difference. So you can, instead of fitting a random forest model, you can use a chi-square plot to know which features are important. So you can see, for example, grade or estrogen status, marital status, differentiate race, stage are not important in this task at all. So that's something you can add. Anyone else with a question? If you have no questions, then I'll stop the class recording there for today.